Hello, in this video we're going to talk about a new distribution called the T-distribution. We're going to use the T-distribution a lot in the coming weeks of our course in different contexts. So I want to motivate why we are using this distribution. Let's begin. One of our overarching goals we've seen in our course is that we use sample information to learn about populations. In particular, we are often using sample statistics to estimate population parameters. And so at the moment, one of our goals that we're going to focus on is estimating population mean mu with the sample mean y bar. The sample mean is known, right? So this is a known statistic. And population mean mu is usually unknown, and that's a parameter. Another way that we can consider or call our sample mean is as a point estimate, because it is, well, a single point. Since that sample statistic is just a single value, well, we know that that sample statistic will not equal the population parameter, right? They're not going to be equal. So we're going to end up creating what's called a confidence interval. So how can we create, we're going to develop, how do we create an interval around the sample mean such that hopefully in that interval will contain the population mean. Sort of most of the time, and I'm going to actually say in most samples. So we want to figure out, how do we create an interval that is carefully constructed so that way we can capture the population mean within that interval. So this interval that we are going to create is constructed as such. This is called a 1 minus alpha % confidence interval, but this is not the formula that we're going to use. I'm just going to motivate why we need the T-distribution. So in general, the way that this interval is created is it's plus or minus from the sample mean some sort of margin of error. So what goes into that margin of error? Well, it's composed of some value from the Z distribution, that's a Z critical value. Remember, alpha is some area in the tails, and here this is saying, well, chop it in half because there's two tails. Multiplied by the standard deviation of the sampling distribution. Remember this, sigma over square root of n. So that is how the confidence interval is constructed when we know sigma. However, we don't usually know sigma. So we are estimating a population mean mu, but what's also typically unknown is the population standard deviation as well. So it may seem reasonable to say, okay, well, since sigma is a population parameter, can't we just replace it with the sample version? Can we just use the sample standard deviation? Well, yes, that would be great. However, this does not come with a little compromise, because the sample standard deviation, what it does is it's going to incorporate additional variability as opposed to if we had just used sigma. So to account for this additional variability, we're going to need to use some new distribution that's called the t-distribution. So the t-distribution is a set or a family of normal curves, and they all have a mean of 0. So a family of curves, that just indicates that there are multiple of them. It's not just one. It looks like a normal distribution, except that there's going to be more variability or more spread in these t-distributions. So I'm going to draw a picture here. If you have the standard normal distribution here in blue, so I'm going to call that Z. And in yellow, I'm going to draw one particular example of a t-distribution. So a t-distribution is going to have more variability. So there's going to be more area in the tails. So the t-distributions have what we call heavier tails or fatter tails than your classic Z distribution. We'll call these heavier tails. Heavier tails. So I had mentioned that there is a family of normal curves that make up the t-distribution. Because there are many different t-distributions, their precise shape, like how heavy are those tails, that precise shape is going to be dependent on something that's called degrees of freedom. So what is degrees of freedom? Well, it's not too difficult. This is just dependent essentially on sample size. I'm going to say df is n minus 1. Sample size, we've seen, plays a considerable role in the reliability of our estimates. We saw that in the sampling distributions in the previous chapter. So there are different t-distributions, and I could even draw another one here onto this curve or onto this image that maybe even has wider or heavier tails. Since there's more area in the tail, that means it's got to make up for it by coming down shorter in the center. Now that one's very flat looking, but I hope you get the picture there. I could even draw another curve. Let's see, let's go with green. Now this one I'm going to illustrate is very close to the blue Z distribution. So I'm going to kind of make it almost indistinguishable. It's almost hugging it very closely, the blue curve. So this image is now getting a little crowded. However, we can see that these all are normal curves. They all have a center of 0, and the spread is dependent on this thing called degrees of freedom. And so as the degrees of freedom, it's just sample size minus 1, as that degrees of freedom increases, the t-distribution will look more and more and more like a standard Z distribution. So they have a lot in common, but we are now going to use a new t-distribution in order for us to have more reliable estimates when creating this thing called a confidence interval. And while we're here, I would like to make a distinction on some terminology. We've discussed standard deviations of two types of sampling distributions. We've got the standard deviation of the sample mean and the standard deviation of sample proportions. And these are both features of the sampling distribution, and they're theoretical, as typically sigma and p are population parameters that are unknown. However, these are used as ways to estimate the precision of these statistics. So these are ways to quantify the precision of the sample mean and the sample proportion. However, these are unknown. Therefore, we estimate them by something that we're going to call standard error. And it's basically a replacement of the unknown parameters with their sample counterpart. So the standard deviation of the sample mean is replaced with standard deviation over sample size, square rooted. But that's the sample standard deviation. And then the standard error that estimates the standard deviation for the sample proportion sampling distribution is replaced with the sample proportion instead of the population proportion. So thought I'd throw that out there so that way we have some of our terminology straight. The word standard error is a nice abbreviation to the phrase an estimate for the standard deviation of these sampling distributions. In the next video, we'll learn how to work with the t-distribution by using the t-table and maybe even a little bit of R.